All right, so we are looking at a Chapter 3 review. Over here. Chapter 3 review for Workplace Math 20. And in Chapter 3, we're talking about surface area, volume, and capacity. So first of all, surface area, as you know, is literally the area of all of the surfaces of a three-dimensional figure. So if we're talking about a cube or about a rectangular prism, then we're talking about the area of this side, plus the area of this side, plus the area of this side, plus the area of the back side, the other side, and the bottom. So we're talking about adding up all of the areas of the surfaces, okay? Add up the areas of the surfaces. Volume is how much space a 3D object takes up. So when we're finding volume, for prisms, it's base, the area of the base, times the height for prisms. And remember, prisms are shapes that have an identical top and bottom. So it's like a square, and then it's like that square is pulled up, another square on top, and they're identical top and bottom. Okay? That's a prism. And we'll get into the other shapes, pyramids and cones and spheres and all that sort of stuff too in this review. Capacity is, it's very similar to volume, but capacity is usually in different units like milliliters or liters, and it's units that a liquid would occupy. So when we're talking about centimeters squared, that would be a volume. If we're talking about milliliters, that's an equivalent capacity. Okay, so milliliters and liters and stuff like that is capacity. So actually, in the real world, you don't see, give me that 2 square decimeter Coke. No, it's give me that 2 liter Coke, right? So in order to make those connections, that's why we're studying that here. All right. So obviously there are some formulas that you need to know for this exam coming up. The area of a rectangle is length times width. It's just this side times this side, okay? Length times width. The same for an area of a square, length times width, but the square happens to have all sides the same. So it's kind of like the side times itself, side squared, area. The area for a parallelogram, and this is a bit strange, and I don't know how many questions you've done where you've had to find the area of a parallelogram, but really the area of a parallelogram very similar to a rectangle in that it's the base times the height. Now the height is this height. It's not the length of this side like it is for a rectangle, it's the vertical height. So one base times the perpendicular height there. That makes a 90-degree angle with the base. So base times height, same for parallelogram. Triangle, formula, area of a triangle is 1/2 the base right here times the overall height. Okay, from the base all the way up to the opposite point. That's the height. So area is 1/2 base times height. Again, you've learned these years ago, so hopefully in working in this chapter, now that you know all this real well. Circle. So the area of a circle is pi times the radius squared. Area is pi r squared. Also very important. Trapezoid, you won't run into this very often, but the area for a trapezoid, and you can write this down in your cue sheet, whatever you want to do. The area is 1/2 the sum of the two sides that are parallel. So in a trapezoid, there'll be two sides that are parallel to each other. 1/2 the sum of a plus b times the overall height. Okay, so 1/2 a plus b times the height. That's the area for a trapezoid. All right, so those are some main formulas that we'll need to know. And you'll get questions just like this where you'll have to find the area for a two-dimensional figure. So area for a sphere, right? The area for, a circle is pi r squared, right? And this is the radius. This triangle here, the reason why we have a dotted line outside here is because that's the overall height of the triangle if this is the base. So this is the base right here, and this is the height over here, okay? This is not the height, like from here up to there. That's not the height. This is not the height, as you can probably tell. It has to go from the opposite sort of point down to the side that's the base or an extension of the side. So that's where this gets a little tricky, something like that. But you can kind of see that the base and the height have to make a 90-degree angle here. The base length of the triangle and the height. All right. This would be the base on this, 14.8 would be the base of this parallelogram, and 5.3 would be the height. Remember, the base and the height have to make a 90-degree angle. And here the base is 16 while the height is 9, making a 90-degree angle, those two. Base and height always have to make a 90-degree angle. Any questions on those first two pages? All right, moving on. On page 129, you're given an example like this where you're asked to find the area of some strange diagram. And this is like a composite figure where you can split this. Usually there's a number of different ways you can split it, but you can split it into shapes that you know the area for, and you have to combine them. So here's a rectangle right here. So you can find this area. Here's another rectangle. You can find this area, and here's a triangle. And you can find this area, and you can add them up. And you might have to do a little bit of, thinking. Like for example, this right here, what is this length? It's not given. Well, it's 3.1 plus 6.8. You see, it's this side plus this side. And what is this side right here? Well, it's 13.4 minus 6.2. That's what this side is. So you can kind of figure out how to add or subtract other sides that are related to get the lengths you need. And of course, 12.6 would be the height of this triangle if this is the base right here. Okay? So that's just a bit of review. Take any strange object and try and split it up into known shapes and then find those areas separately. And go, just throw up your hand or just interrupt me if you have a question. I'm just going to kind of go through this just like it's a review. Kind of like, yeah, I know that, Mr. Maxwell. Yeah, that's good. But if you want me to pause at any point and explain something further, now is your chance, okay? All right. Some terms here, okay? A prism, like I mentioned already, it's a 3D shape where the bottom and the top or the ends are the same shape. Either they're both circles or they're both squares or they're both rectangles or they're both triangles that are identical. All right. A lateral face is another term that we need to understand. So here, let's say this diagram down here, if this is the base, then the lateral face, this is one lateral face right here. This is another lateral face right here and another lateral face. You see that? So lateral means kind of the sides. If you have a top and a bottom, the lateral faces are the sides. Okay? So again, this triangle and the other triangle at the other end would be the top and the bottom. And the lateral faces would be the sides here of this triangular prism. See, that's called a triangular prism. Questions? Okay, a net diagram. We've talked about net diagrams before. If you took a shape like this that's meant to be a three-dimensional shape and you're asked to make a net diagram, you'd want to draw the front and the back, or the top and the bottom, whatever, and you'd want to draw them down three-dimensionally and attach the bottom and the sides accordingly. So I won't go over net diagrams too much because we've been over that quite a bit already, but you will be required to maybe draw some net diagrams. They will help you to make sure that you don't miss anything when calculating the surface area. Okay, so net diagrams are important in calculating surface area. I think we went over this question too in the lesson. These two net diagrams are for the exact same shape. Okay, here we have an octagonal base and an octagonal top. They're connected by one of the sides. And the sides are connected to each other, like drawn over here. Whoops. They're connected to each other, but they're also connected to either the base or the top, see? Just like that. So you could draw a net diagram a number of different ways. You know, it's not really just one right or wrong way to draw a net diagram necessarily, as long as you have everything taken care of. I would encourage you to label your net diagrams, to try and draw them also to scale a little bit so that you can identify which sides are the same, top, bottom, front, back, and so on. Okay? Any questions? All right, I went over this one here. I guess we're talking about surface area here as well. We're going to get into volume here pretty quick, I think. Before we get into volume, let's talk about surface area for cylinders and spheres and cones. And so obviously, I think let me go back. A cylinder, right, is basically a right circular prism. It's a circular prism where the tops and bottoms are circles, right? You know that? That's a cylinder. A sphere is a three-dimensional ball, right? It's like a circle that's three-dimensional, a ball. A sphere is a ball. And a cone, if you recall a cone, it is a circular-based pyramid. And I kind of skipped over the pyramids there as well, but the pyramids have some kind of shape on the bottom, and that shape could be any one of things. But it's different than a prism in that the top and the bottom are not the same. The top is always a point in a pyramid or a cone. The top is always a point, or the bottom, one of the ends. And then you have some kind of shape on the other end. So this would be a prism here, a square bottom prism, let's say. Prism. Okay, so pyramids and cones are very much the same. The surface area is a little bit different in calculating that, which we'll go over in a second. But the volume, when we get to volume, calculating the volume for surface for cones and pyramids are virtually identical. All right, a lot to cover yet, but we'll go through this as quick as we can. All right, what's next here? This would be some kind of figure that you would have to find the surface area for. And again, you see a rectangle with a half of a circle cut out. So you're going to have to take pieces at a time, find the area of the rectangle, subtract the area of half the circle that would fit in there, right? Half of a circle would take out. Okay, so surface area of a cylinder. Okay, what do we need to remember here? Well, the top and the bottom are circles, no problem. So we've got 2 pi r squared, right? That's 2 circles. So the surface area for a cylinder is comprised of 2 circles. Also, this wraparound base, and again, I went over this in the lessons, but the length of the wraparound part is the same as the circumference of the circle. So the circumference is 2 times pi times radius. That's the length of the wraparound part. And then, of course, to find the area of that, you multiply by the height. So 2 pi r h. This is the surface area for a cylinder. The 2 circles on top and bottom and the wraparound part. All right, getting into pyramids. Again, if we're talking about surface area, find separately the surface area of the base and then all the sides. And drawing net diagrams sometimes really help out here. So as you can see from a square bottom base, you can draw the sides that would fold up, or fold down like a flower, right? And so you would take the surface area of this square, 24 by 24, and then the surface area of each triangle. And this would be the 24 is the base here, and the height looks to be 16 here. So 1/2 base times height is the area of one of the squares times 4 would be the area of all this, the triangles there, sorry. All right, so surface area of a pyramid. Pretty straightforward. Hopefully you've done your work on that. Now, cones, surface area of cones. This one is a little bit different. We drew a net diagram for a cone. Obviously, it has a circular base. The wraparound part for a cone, when we're talking about a net diagram, looks a little funny. It kind of has this rounded part here. That's what a net looks like for a cone. And obviously this is pi r squared, the circular base, and the area for this wraparound part is pi times r times s, where s is the slant height. So s is from the point down the length of the side here. So from here all the way down to there. That's s. Okay? Surface area of a cone. So the overall surface area is pi r squared plus pi r s. That's the surface area for a cone. Any questions about that? You guys being very quiet. So I'm assuming that you're like, I understand this. This is all totally familiar. I've been through this. Okay, good. I'll assume that is the case. So we're about 2/3 done here. What I have planned. Surface area for spheres. Okay, this one's a bit strange. Again, I don't really have a great explanation, I don't think, about where this comes from. Maybe one of you could look that up, but I haven't really been able to find a real good explanation as to why the surface area for a sphere, other than just repeated patterns and observation and experimentation. It's been determined that the surface area for a sphere, okay, is 4 times pi times r squared. So if you were to cut a sphere up, if you had a ball made of paper or something, and you were to cut it up and lay it down, and I'm not even going to try here to draw it, but it would be equivalent to the area of 4 circles, the 4 circles that would lay just inside in the middle of the sphere. So whatever that circle is, it would be like 4 of those. That's what the actual wraparound part ends up to be equal to. Okay? So the surface area for a sphere is equal to 4 of the circles that you could fit inside perfectly in a sphere. Just got to remember that. 4 pi r squared. Okay? All right. Now, if we have a semisphere or a hemisphere, where you have like a flat bottom and then just half of a sphere that's cut off, well, that's a little bit different then. The wraparound part around the outside there is 2 pi r squared because it's half of a full sphere. But then you have to add the circle that would be on the bottom. And I have a hemisphere right here. So some of you have already worked with this. You've seen that, but this is like a hemisphere. So the wraparound part, and you can see that on the screen maybe for those of you that are too far away, but the wraparound part here is 2 pi r squared. That's what this wraparound part is. And then the bottom is 1 pi r squared. So 2 pi r squared plus pi r squared is same as basically 3 pi r squared. That's the surface area for a hemisphere, if you're counting the bottom. All right, so 3.3 is where we get into volume and capacity. As I mentioned, volume is the measure of the space that an object takes up. Capacity is the amount that this 3-dimensional object could hold as far as like a liquid or something like that. That's the difference. And the units are the big thing. Usually it's like centimeters cubed or meters cubed versus capacity would be something like milliliters or liters, something like that. Yeah, question?
Is it possible to get a page with all the volume equations on it?
All right, so volumes for prisms, like rectangular prisms, are simply, length, like length times width times height. Length times width times height. If you're given a composite object like this, you would need to split it up into known prisms. So length times width times height would be, for a cube or something like that, right? Length times width times height. That's the volume. Volumes of cylinders. Okay, so volumes of cylinders. Really, cylinders are just circular right prisms, right? I mentioned that before. So you take the area of the top and you multiply it by the height. So really easy. So volume is, for a prism, is area of the base times the height. For a cylinder, the area of the base is pi r squared times height. So that's the volume of a cylinder. Pi r squared h. Here's a bit of a note here. Remember that 1,000 cubic centimeters equals 1 liter. And I believe that somewhere in the lessons I have kind of written down something. I'll do it again. So 1,000 centimeters cubed is equal to 1 liter. 1 centimeter cubed is equal to 1 milliliter. Those are the 2 important things. If you know those, you're good. Okay, really, this is the base one. Everything comes from this. 1 centimeter cubed is 1 milliliter cubed. Let me know if there's any other conversions you need to know about, okay? Milliliters, liters. Not sure what other capacities really we're dealing with. But okay? Now, 3.4, let's see. Okay, volume of spheres. So here's the formula for volume of a sphere. 4/3 pi r cubed. 4/3 pi r cubed. Let's see. Oh, I don't have the page that actually has a sphere written on it. But a sphere, remember, is a ball, 3-dimensional. And the volume is 4/3 times pi times r cubed. Remember that the units for volume are always units cubed. For surface area, the units are always units squared. Okay? An important thing for you to remember also as we move here. And I think the final thing we need to talk about, just by way of quick review here, are the volumes of pyramids and cones. Okay? If you didn't get that formula down, if you want me to go back, I can go back when I'm done here. Okay, the volume for a pyramid. Okay, so we talked about this. A prism, right, has the same bottom and the same top, right? A pyramid has a point at the top. So if you look at these two, obviously the volume of this one is going to be much bigger than the volume of this one, right? Because this pyramid could fit inside of this prism like this. And obviously it doesn't occupy as much space. And the factor is this is 1/3 the volume right here, the pyramid. So you take the volume of a pyramid is the area of the base times the height divided by 3, because of the factor it's only 1/3 as big. So it's the area of the base times the height, and the height of course would be from the center of the base to the tip. Not this side of not the side, but the center to the tip, and divided by 3. Prism is this one. This is the prism. This is the pyramid. Yeah, the prism is the same bottom and top. They're the exact same shape. So it's kind of like just stretched up, and it's 90 degrees and all that sort of stuff. Bottom and top are the same. The pyramid, all the sides come to a point. So we're talking about triangles really on the sides for pyramids, right? Okay. So a volume of a pyramid would be the same as the volume of a prism, but divided by 3. So it makes it really easy for a cone. So consider a cone, right? A cone. Now I don't have a diagram here. Okay. Yeah. So a cylinder is a circular prism. There's a cylinder versus a cone. Looks like this, and again, it's like a pyramid, a cone, a circle pyramid, comes to a point. So guess what? This is exactly 1/3 of the volume as well as the cylinder with the same size base. So the volume for a cone is the area of the base, that's pi r squared because it's a circle, times h, which is the overall height, divided by 3. Perfect. Okay, and this is for a cone. So remember, cones and pyramids are virtually the same thing. They're virtually the same thing. For volume, it's the area of the base times the height divided by 3. That's the same for cones and pyramids. And of course, for the cylinders, the volume for a cylinder is pi r squared h. That's all it is. Pi r squared all the way up. This one is pi r squared h, but it's divided by 3, so the circles keep getting smaller as it comes to a point. You see that? So it doesn't occupy as much space. Any questions? Any questions at all? And there's that part of that conversion thing, right? See the conversion thing? That's the capacity conversion. Okay, so that's a quick overall run of Chapter 3. If you have any specific questions, feel free to watch an instructional video, or if you're in my class here today, as soon as I'm done this, you can ask me any question you want. Okay? All right, so that is Chapter 3, Workplace 20.
Subscribe.
Like.
Comments.
Go to mrmathwell.com.